Welcome to AI Paper Podcasts. We're the show that helps you get that competitive edge by really digging into the latest AI research and breakthroughs.
And today, wow, we're looking at a paper making a pretty bold claim, basically the GPT-3 moment for machine vision.
That's right. We're talking about how video generation models are moving beyond just, cool tech demos.
Exactly. Becoming these general-purpose foundation models. Think less parlor trick, more fundamental tool.
And the focus today is this deep dive into VO3, a real state-of-the-art generative video model. The research suggests it's developing genuine, broad visual understanding.
Yeah, capable of tackling vision tasks zero shot, like right across the computer vision stack without specific training for each one.
Okay, so if you just need the quick technical rundown for your weekly sync, here are the absolute key takeaways. Hold tight.
Okay, first up. VO3 showed these emergent visual skills across, get this, 62 different qualitative tasks and 7 quantitative ones.
62, wow.
Yeah, and the crucial part, it did this with zero fine-tuning or specific adaptation for those tasks, just prompted.
Okay, second big thing. This idea of early visual reasoning is popping up. They're calling it chain of frames, or COF.
Yeah. Think of it like chain of thought, but for vision. It's how the model seems to solve sequential problems, like figuring out a maze, one frame at a time.
It's super interesting. And the third point.
Right. Third, the performance jump from the previous version VO2 to this new VO3 is just massive and fast.
Okay.
And that speed really suggests these generalist models might actually start replacing specialized, bespoke computer vision systems sooner rather than later.
Okay, let's really unpack that shift then. We've talked for ages about how large language models, LLMs, became the blueprint for foundation models, right? We got that general understanding by training huge generative models on just tons and tons of web text. But vision felt kind of stuck for a while.
Totally stuck. I mean, if you're an ML engineer doing CV work right now, you're probably juggling a bunch of different tools, aren't you?
Yeah, like anything for segmentation. Maybe some custom YOLO model for detection, another thing for depth.
Exactly. A whole patchwork. Each tool does its one job okay, maybe even great. But the whole system isn't flexible. You can't just ask it something new easily.
It really is like NLP before Transformers, before GPT. You needed separate models for translation, Q&A, summarization, all siloed.
And this paper's whole argument is apply the exact same recipe to vision. Massive scale, massive video data in this case, and a generative goal.
And you get the same outcome. A generalist model.
Right, and that generative objective is so important because to generate a realistic video from just an image and a text prompt, the model has to learn physics, space, time, a deep world model. It can't cheat.
So when we talk about zero-shot learning here, it's the dream, isn't it? No more fine-tuning for every little task.
Pretty much. Instead of training a specific head, for instance, segmentation, you just write a clever text prompt telling the video model what you want.
Like, segment the objects in this scene and show me.
Exactly. Input, image, and text, output. An 8-second video, 720p, 24 frames per second, showing the solution unfolding.
And they picked VO3 because it's consistently topping the leaderboards for text-to-video, image-to-video stuff.
Yeah, it's a strong performer. But what's really wild is the speed of development. VO2 was only announced December 2024, released April 2025.
And VO3?
Announced just a month later, May 2025, and out by July 2025. That kind of iteration speed, it's why this research lands with such impact. It's moving incredibly fast.
Okay, let's get into the qualitative results. This is where you see the model doing things that feel like more than just recognizing patterns.
Right. And the researchers did a nice job organizing the findings. They used this 4-part hierarchy, which actually maps really well to how vision capabilities build on each other.
What a level.
It starts with perception at the bottom, then modeling, then manipulation, and finally reasoning at the top.
Okay, so the perception, the foundation. Can VO3 handle classic computer vision tasks without being explicitly trained? Like edge detection?
Yep. It did really well on edge detection, 0.92 success rate, basically outlining objects clearly. Instant segmentation was okay, 0.33 success rate, showing flat-colored masks. Key point localization, like finding corners of a box, was 0.58.
But what really caught my eye wasn't just the standard tasks, it was the ambiguous images they threw at it.
Yes, like the Dalmatian illusion.
Spotty dog picture.
Exactly, where your brain has to kind of fill in the gaps to see the dog, and even Rorschach ink blots.
Yes. That's pretty deep. It suggests the model isn't just plotting pixels.
Right. To get the Dalmatian, which it did, it needs some kind of, gestalt processing, seeing the whole structure from messy parts. That's way beyond basic feature extraction.
Okay, so building on that perception is modeling.
Yeah.
This is about the model's grasp of intuitive physics and how the world works.
Exactly. It doesn't understand basic reality. And it showed pretty solid results. It could model soft body dynamics like draping a silk scarf over a vase. That got a 0.67 success rate.
Which needs gravity, friction, material understanding.
And understanding material properties too, like flammability or buoyancy, though the success rates were lower there, like 0.25 for flammability. Still, the attempt is notable.
The optical stuff was kind of mind-blowing, though.
Oh, totally. Modeling reflections off a mirrored sphere. Perfect success, 1.0. Refraction, light bending through glass. Almost perfect, 0.92.
Think about that. It learns an intuitive physics engine for light just by watching videos.
It's incredible. And not just physical laws, but things like color mixing too. Additive color, like lights, 0.92 success. Subtractive, like paints, 0.75.
So it's learning the rules of the visual world, physical and abstract, just by observing.
Pretty much. It's building that internal world model. It even did okay at abstract categorization, like putting kids' toys in a bucket, 0.33 success rate.
Which brings us up the hierarchy to manipulation. Can it use that perception and modeling to actually edit scenes or imagine changes?
Yes, and quite well on standard stuff. Zero-shot image editing, like background removal, 0.83 success. Style transfer, like making a photo look like it was painted by Hundertwasser, 0.75 success.
Tasks usually needing specialized models.
Right, and it can do in-painting and out-painting perfectly, 1.0 success. But then it gets more creative.
Like
Generating novel views, like rotating an object smoothly in 3D space, 0.92 success rate for that. It even tried really abstract stuff, like morphing a teacup into a mouse.
Okay, how did that go?
Low success, 0.17. But the fact it attempts these complex imaginative transformations signals something more than just imitation.
And it handled simulated dexterity, like a robot hand doing something.
Nailed it. A robot opening a jar simulation. 1.0 success rate. It understands the necessary sequence of actions visually.
Okay, so that leads us to the top. Reasoning. Powered by this chain of frames idea, COAF.
Yes, applying all that knowledge across time and space to solve visual puzzles step by step.
Let's explain COAF a bit more, because that feels like the really new, crucial link here. How is it different from just generating a video?
Okay, so COAF implies the model isn't just generating the final frame or the whole clip in one go. It's using the frame-by-frame generation process as its thinking space.
Like an internal scratch pad.
Exactly. Each frame generated is an intermediate step. If it's solving a maze, frame 1 might be entering, frame 2 moving forward, frame 3 hitting a wall, frame 4 turning. It's visualizing the solution path.
And course correcting visually as it goes.
That seems to be the idea. Just like chain of thought in LLMs uses intermediate text steps to refine logic, Co uses intermediate visual frames.
And the examples they showed really back this up.
Yeah, pretty strongly. Things like completing visual sequences, patterns of shrinking circles or arrows moving it got high success. Up to 1.0, shape fitting was harder, 0.25.
And tool use.
Almost perfect. Using tongs to get a walnut out of an aquarium, 0.92 success rate. The generated video is the evidence of the step-by-step visual plan.
Okay, let's pivot to the quantitative stuff.
Okay.
Section 3. Comparing VO3's numbers against other models.
Yeah.
This grounds the hype a bit.
Right, puts it in perspective. How does this generalist really stack up against specialized tools?
And they make this important technical distinction first between best frame and last frame metrics. Crucial for our technical listeners.
Yeah, that's a good point. So best frame is like the model's peak performance within the generated video, the single frame where it did the task best.
Potential ceiling.
Exactly. Whereas last frame is the practical output. What does the video look like right at the very end? If the model solved it midway, then messed it up, the last frame score drops.
So it measures potential and reliability. Makes sense.
So looking at perception benchmarks, take edge detection measured with OIS, optimal image scale. VO3 gets 0.77 pass at 10.
Can you quickly remind us what pass at 10 means?
Sure, it means they gave the model the prompt 10 times and counted how many times it succeeded. It measures how reliably you can get a good result with a few tries.
Got it. So 0.77 zero shot. How does that compare?
Well, a dedicated state-of-the-art edge detector might hit, say, 0.90. But here's the really interesting part the researchers found.
What's that?
Sometimes VO3 failed the benchmark because it produced more detailed edges than the ground truth dataset had, like outlining individual leaves or tire treads the dataset ignored.
So the dataset labels might be the bottleneck, not the model's actual perception.
It suggests that, yeah, the model might be seeing more than the benchmark asks for.
Okay, what about instance segmentation, measured with MIOU?
There, VO3 got 0.74 pass at 10 on the best frame metric, which is actually very close to a specialized image editing model like Banana, which scored 0.73.
That's impressive comparability for a generalist video model doing it zero shot.
It is, and they found a fascinating technical detail here too. Prompt bias.
How so?
It did significantly better when prompted to put the segmented object on a green background, 0.74 MIOU, compared to a white background, 0.66 MIOU.
Huh. Like it's learned from green screen data.
That's the strong suspicion. It shows how those training data priors can really leak into performance even on these zero-shot tasks. So you have to be aware of that.
But the real quantitative win seems to be in reasoning, proving that COVID advantage maze solving.
Huge difference here. On 5x5 mazes, VO3 hit 78% pass at 10.
Okay, and VO2, the predecessor.
Only 14%, just a massive leap. The VO2 often failed because it would make an illegal move early on and couldn't recover.
While VO3, using COF,
seems to be able to visually check its path frame by frame and avoid those early fatal mistakes. It plans better visually.
And how did it compare against language models trying the same visual task?
Great comparison. They tested Gemini 2.5 Pro. When given the maze as ASCII text to text, Gemini did okay.
But when given the maze as an image to text, and asked to describe the path,
performance plummeted. It really struggled.
which strongly suggests
That trying to translate an inherently visual spatial task like pathfinding into language just loses too much information or adds unnecessary complexity. VO3 solves it in the visual domain, step by step. That's its advantage for these kinds of problems. Visual symmetry completion showed similar big gains over VO2 and Banana too.
Okay, implications. Let's talk about that. The paper calls it a GPT-3 moment, which is exciting, but we've heard that before.
Right. Healthy skepticism is good.
And they admit VO3 is still a jack of many trades, master of few. It lags the specialized SOTA models by 10, 20 points sometimes. So why ditch our finely tuned specialist models for this generalist that's, only 70, 80% there?
Yeah, that's the million-dollar question, isn't it? If you need 99% accuracy for, say, medical imaging or quality control on a production line, 78% isn't cutting it today.
So the argument isn't about today's performance.
Not entirely. It's about the trajectory. That leap from 14% to 78% in maze solving between VO2 and 3 happened in just a few months. That suggests incredibly efficient scaling.
So the bet is that the performance gap will close fast, just like GPT-3 quickly caught up to specialized NLP models back in the day.
That's the bet. And remember the pass at 1 versus pass at 10 results? Performance consistently improves with more samples.
Meaning the capability is latent.
Exactly. It suggests that with better inference time techniques, maybe sampling strategies, and especially instruction tuning and RLHF adapted for video, that remaining 20% gap could close very rapidly.
Which leads us straight into prompt engineering for vision.
Yeah.
It's clearly not just a nice to have anymore, it's critical.
Absolutely mission critical. They did a sensitivity analysis on the visual symmetry task. Get this. The difference between the best prompt and the worst prompt was 40 to 64 percentage points.
Wow. So a bad prompt makes the model look completely broken.
Totally. It highlights how crucial freezing is.
So what did they find works best? What are the practical tips for engineers?
Okay, number 1, kill ambiguity. Don't just say make it symmetrical, specify how. Symmetrical along the vertical axis. Be precise.
Makes sense. No.
Number 2, specify constraints. If you need a static shot for an editing task, you have to say static camera, no zoom. Otherwise, the model's default is often to add camera movement because, well, it's a video model.
Okay, got it. And you mentioned this subtle trick, the motion outlet.
Yes. This was clever because the model wants to generate motion. If you need a mostly static scene, like for image editing, give it a small, unimportant thing to animate, like telling it to have a tiny ball spinning in the corner. That satisfies its need for motion without messing up the main part of the scene you care about.
That's a great hack. And the last tip, realism.
Yeah, grounding abstract tasks. If you have a geometric puzzle, phrasing the prompt to describe it as a realistic physical setup like kids' blocks or a toy puzzle often helped performance significantly.
Why?
It likely connects the abstract problem back to the model's core world model, which was learned from tons of real-world video. It helps it understand the spatial relationships better.
Okay, last big piece, economics. Generating video is computationally expensive right now, much more than text or static images. Why should companies even look at this now?
Cost is definitely a factor today. But the paper rightly points to the cost curves we've already seen play out with LLMs.
They drop fast.
Incredibly fast. LLM inference costs have fallen by factors of 9x to even 900x per year in some cases. There's every reason to expect similar scaling economics for video models.
So the initial high costs will likely become much less of an issue relatively quickly.
That's the projection. Early LLMs were also really expensive, but they rapidly became cost competitive and often cheaper than maintaining lots of separate, specialized NLP models. The bet is the same happens for vision.
Okay, so wrapping up, VO3 doing zero shot across the whole vision stack, perception, modeling, manipulation, even this nascent reasoning really does feel like a major signal. The foundation model paradigm seems to have truly arrived for vision.
It really does. A potential game changer for anyone working in ML or CV.
We're seeing reasoning emerge through this chain of frames mechanism, which is super exciting for things like robotics and automation simulations. But there's still gap, right?
Definitely. The paper itself mentions where it still fails. Like, it can generate a video showing tongs picking up a walnut, but it struggles to generate usable step-by-step visual instructions for really complex real-world tasks.
Like folding laundry from visual instructions, or figuring out the precise way to angle a sofa to get it through a narrow doorway.
Exactly. Those tasks require not just visual simulation, but understanding precise kinetics, friction, collision avoidance in the real messy world.
So that brings us to our final thought for you, our listeners, especially those working in this space. If Chain of Frames lets models reason visually within their generated simulations, what's missing to bridge that gap to reliable, real-world physical instruction following?
Yeah, what architectural changes or maybe data modalities or training objectives beyond just making the models bigger do we need to go from simulating visual reasoning to actually instructing complex physical actions reliably? What do you think is the next piece of the puzzle for the vision stack?
Something to definitely chew on. That's all for this episode of AI Paper Podcasts. Thanks for tuning in.
Thanks, everyone.